In this video, we'll do an optimization example in which we minimize and maximize a certain sum. So the problem says the sum of two non-negative numbers is 15, and A asks, find the minimum sum of the square of the first number and the product of 4 and the square of the second number. B says, find the maximum of the sum in part A. Okay, so I want to break down these optimization questions. Remember, optimization just means either to minimize or maximize something. And in this problem, we want to do both into steps. Okay, so step 1 in an optimization problem will be to identify the quantity that we want to maximize or minimize. To maximize or minimize. So in some optimization questions, we'll just be maximizing something. Sometimes we'll just be minimizing something. In this problem, we're going to do both. Okay, and this problem says there's this certain sum. So we're going to do it to a certain sum. All right, so we are on to step 2. We've identified the thing that we want to maximize or minimize. We are ready for the next step. So step 2 is much like with the related rates. We draw a picture. Draw a picture, if applicable. And we assign variables. In this problem, I don't think it makes sense to draw a picture, but we can assign variables because it talks about this first number, this second number. So maybe I'll call the first number x. Maybe we can call the second number y. And then it also talks about a certain sum. We're going to sum the square of the first number and the product of 4 and the square of the second number. So ignoring, most of those words, we'll get to them. It talks about this sum, a certain sum, and let me call that sum s. All right, so we are ready for step 3. So step 3, now that we have our variables assigned, is to write an equation, we'll just abbreviate equation, for the quantity that we want to optimize, and that means either maximize or minimize, for the quantity that we want to optimize. And this is called the objective. It's called the objective equation. So I'm going to underline that key term, objective. So let's think about what the objective for our problem would be. So I'm going to zoom out a little bit. Our objective is an equation for the thing that we want to maximize or minimize. And it's the sum that this problem is describing. Okay, so I'm going to call it S. We already decided S for the sum. And so we're going to be summing two things. So something plus something. And what I know is that second thing, it says the sum of, well, let me break it up into pieces. It says the sum of the square of the first number. So I know what goes in the first box is x squared. And so the and will represent that plus sign. It'll separate, the first term from the second term that we're adding. And let's see, the product. So product means I'm going to be multiplying two things. So it's going to be plus, and then something times something. There's going to be a product in here. So it's the product of 4 and the square of the second number. So I should be putting a 4 there, as well as the square of the second number. So 4 and the square of the second number, we're calling the second number y. So 4y squared. So that is the thing that we want to maximize and minimize, this equation for s. All right. And the way I remember this term objective is, it is my objective or my goal to maximize this and to minimize this. That's why I remember objective. I think, oh, it's my goal. My goal is to maximize this thing or minimize this thing. All right, so we are ready for step 4. So the difficulty with trying to maximize or minimize this thing right now is on the right-hand side, we have two variables. We're used to finding the max or min of a function that's in terms of one variable. So we need to somehow get this in terms of one variable. So we will get the objective in terms of one variable. I'm going to put a squiggly line underneath the one variable. I'm going to emphasize that using other info in the problem, and this other info is called a constraint. So I will call it the constraint equation. We use other information to write down some equation, and once we have that, we will substitute. So if we look back to the problem, there is some other information that's given to us. It tells us the sum of these two non-negative numbers. Well, by the way, it tells us x and y are non-negative, which means x is greater than or equal to 0, and y is greater than or equal to 0. So the sum of those numbers is 15. Okay, so that is another piece of info. This is going to be my constraint. So my constraint here is that x plus y is equal to 15. So let's isolate one of the variables in this equation. Typically, we will isolate whichever is like easiest to isolate, and then I will plug that into my objective. In this case, I think both of the variables are equally easy to isolate, so maybe I'll isolate x. So x equals 15 minus y, and now let's substitute. Let's substitute this. So if we substitute, we get s equals, so we're going to plug in for the x, so we will get, we're plugging in 15 minus y, we'll get that squared plus 4y squared. All right, now we have a function in terms of one variable. We know how to maximize and minimize things like this. The first step to doing that is we find the critical numbers. We find the critical numbers, and then we'll have to test whether we have a max or min at those critical numbers. Okay, so let's first simplify this. I'm going to do 15 minus y times 15 minus y. That'll give me 225 minus 30y plus y squared plus 4y squared. And this becomes s equals, let me put the y squared terms first. So 5y squared minus 30y plus 225. All right, and now we are ready to take the derivative. Okay, so because the variable in this function is y, we're going to take dy on both sides. So on the left-hand side, that'll give me ds dy. Okay, and on the right, we'll just get the derivative of this thing like normal, which will be 10y minus 30. So we got our derivative. We need to now know when is this going to be equal to 0, and when is it going to be undefined. So 10y minus 30, this equals 0. When, if I rearrange this, if I add 30 to the right and I divide by 10, we'll get y equals 3. Okay, and when is this undefined? Well, this is never undefined. There's no denominator or anything like that, so I don't worry about, there's no value of y I can plug in that would make this undefined. Like, I never have a denominator being 0. All right, so my critical number here is going to be y equals 3. So we are ready for step 6 now. Step 6, we want to test our critical numbers to see if they are absolute maxes or absolute mins. So I forgot to mention this earlier, so let me mention it now. But in this problem, when it said find the minimum sum, and then B said find the maximum sum, it didn't specify whether it means local or absolute. When a problem does that, if it just says the word find the minimum or find the maximum, it means absolute. It means what is the minimum, the very smallest value of the sum, or the very biggest value of the sum. So in this problem, we are finding absolute mins and absolute maxes. So that'll be important. Okay, so how do we do this? How do we test our critical numbers? We actually know 3 ways. So there's 3 p.m. So 3 ways to do this. And I'm going to talk about all of them. All right, so method 1 is if we have a closed interval. So if we have a closed interval, we have this method for testing for absolute maxes and mins on that closed interval. So in this case, well, we got our function completely in terms of the variable y. We had s completely in terms of the variable y. So let's think about what's the smallest y could be and what's the biggest that y could be. All right, so in this problem, let me just go back here. Alrighty, so we know with y, it was non-negative, which means it's greater than or equal to 0. But the biggest it could be is 15, because remember, x plus y has to be 15. And if y was something bigger than 15, like if it was 16, that would make x be a negative number, but x has to be non-negative also. Okay, so y is in between 0 and 15, inclusive. It can be 0 and it can be 15. So as an interval, it's in the interval from 0 to 15. This is a closed interval. All right, remember our method for absolute maxes and mins on a closed interval. To find them, we plug the endpoints and the critical numbers into the original function before we took the derivative. That was s here. All right, so we're going to have to plug in the endpoint 0 and s. We get our critical number 3, and we'll have to plug in the other endpoint 5. Or sorry, it's 15. 15, okay. So if I plug 0 into my original function, remember I'm going to use s of y equals, after I had plugged in, it was like 15 minus y squared plus 4y squared. So I'm going to be plugging into that when it's completely in terms of y. So if I plug 0 in, we get 15 squared plus 4 times 0 squared. If I plug 3 in, we'll get 12 squared plus 4 times 3 squared. And if I plug 15 in, we get 0 squared plus 4 times 15 squared. So working these out, the first number is 225. The next one is 180. And the last one is 900. All right, so remember, the smallest of these is the absolute min. The biggest of these is the absolute max. So we are ready for the final step, which is to answer what the question wanted. So answer the question. And remember, the question was just asking, what is the minimum sum and what is the maximum sum? So it didn't want to know the values of x and y. It just wants to know, well, what's the minimum output or the maximum output of the sum? Okay, so let's make sure we do that. So the minimum sum was the smallest of these outputs. It's the 180. So that was the answer to A. And B wanted the maximum sum. And that's the largest of these outputs, which is 900. Alrighty, and those are our answers. So the 180 again, this was the absolute min value, whereas the 900, this was the absolute max value. So even though the question didn't ask for what were the numbers, the x and the y values that gave me the min or the max, if I needed to get them, I could get them very quickly. So for example, for the minimum, this corresponded to when y was 3. And if y was 3, that would mean that my x value, because the y and the x have to add up to be 15, x plus y equals 15. If I were to plug the y value into this, I could see x is definitely 12. So when y is 3 and x is 12, those are the values of these numbers that give us this minimum sum. So I mentioned earlier that there were 3 ways that we could test our critical numbers, and this is just the first. I want to go over the others. Okay, so the second is to use the first derivative test plus a little bit of justification. So remember, the first derivative test was this thing where we do a number line and check the signs of the first derivative. So in this case, remember my interval for y is limited to the values between 0 and 15. So I don't want to bother plugging in things that are less than 0 or bigger than 15 just because y can't be outside of this interval. Okay, and I need to keep track of the sign of my derivative. So my derivative, let me just make a row for that. Or my derivative, remember, was 10y minus 30. Oh, and whoops, I forgot to put a tick mark at my critical number. We had a critical number at 3. All right, and based on my derivative, I'll keep track of the original function s. Okay, and then I'll split up a row and split up a column here. Okay, and if I were to plug in something smaller than 3 into the derivative, it makes it negative. But if I plug in something bigger than 3 into the derivative, it makes it positive. And when s prime is positive, s is going up. It is going to be increasing. And when the derivative is negative, s is going to be going down. It'll decrease. So this shows there's a local min. Remember, the first derivative test is for local mins and local maxes. There's a local min at y equals 3, but we can quickly justify it's also an absolute min, because we need this to be an absolute min in this optimization question. So I couldn't stop here. I got to give a little bit of extra justification, but it's going to be very quick. So how do we justify why this isn't just a local min? Why is this actually an absolute min? So the reason why has to do with the fact that this is a very particular sign chart. So since our original function s is decreasing for all values of y that are less than 3, at least in the interval on which it's defined, and it's increasing. So it's decreasing for all these y values, and it's increasing for all the y values after that. That means that the local min at y equals 3 is also an absolute min. Is also an absolute min. Okay, so let me draw a picture to hopefully help us convince ourselves why that is. So let me draw some axes. So I'll label 15 here, because I'm limited to the interval from 0 to 15, and I'm going to draw 3. That's where I know my critical number is. And based on my sign chart, I know my function, the original function, should be decreasing the whole way from 0 to 3. Got to be decreasing that whole way. And then it's got to be increasing the whole way from 3 onwards to 15. So I don't exactly know which way it's curving, whether it's concave up or down. I just drew a general picture sort of like this. But if that's what happens, if it decreases the whole way until that critical number, but increases the whole way after, not only is that a local min, that is definitely an absolute min. So the very last thing we do is answer the question. And remember, that wanted the actual value of the sum, the output. So we now have to find what s of 3 is. We'd have to plug in y equals 3 into our sum function to get the minimum sum. And we did that already in method 1. We already plugged it in to get that minimum sum, so I won't do that again. So essentially, method 2 here, it works because we just have one sign change in our number line. This number line changed from negative to positive, and that's what made that local min be this absolute min. So one of the downsides to this method is it only gave us one thing, like it only found us the absolute min. It didn't find us the absolute max as well. So if this original problem had just said to find the minimum sum, method 2 would have been just fine. It would have gotten us that minimum sum. But sometimes we may do an optimization problem where it may ask us for a min, but if we do method 2, maybe we get a max. If that happens, it can mean one of two things. Either we made a mistake in our number line, or maybe it was actually a closed interval, and we were supposed to do the closed interval method, because that will find us both, the min and the max. Alrighty, so I mentioned there's one more method, so let's do that third method. Okay, so third method is we can also do the second derivative test plus a little bit of justification. So how does that work? Our first derivative, remember, was 10y minus 30. And our second derivative will then be 10. So with the second derivative test, I take my second derivative and then I plug in my critical number, which was 3. But this is just a constant, so when I plug in, it'll still give me that constant 10. Okay, so in terms of the graph, remember, if this is where 3 is, the second derivative is positive, which is telling me at this critical number, my graph is going to be concave up, so that'll give me a min, technically a local min. So by the second derivative test, this shows that s, our function, has a local min at y equals 3, but we can justify we can justify that it's also an absolute min, similarly to how we did in method 2. Okay, so let's give that justification. So justification. And the way I do this is I will say, since my function s, the second derivative was just 10 the whole way. For every single number I plug in, it's going to be 10, which is positive. So my function is concave up for all values of y. And because of that, the local min at y equals 3 is, if I extend my picture, I've just drawn a really, really tiny portion of the graph here that's concave up, but our function is going to stay concave up the whole way. The whole way. Number until it gets to 0, and then finally until it gets to 15, somewhere over here. It's going to be concave up the whole way. And if that happens, that local min has to be the absolute min. There's no way my function could have turned around to get lower, because if it turned around, it would have had to switch concavity. But this doesn't. This stayed concave up the whole way. So because of that, this local min is also an absolute min. Is also an absolute min. So that's how the justification in method 3 works. So method 3 is similar to method 2 in that it can only find one of these things for us, either the absolute min or the absolute max, depending on the problem. And if a question just asks for one thing, then typically using method 2 or method 3 will be fine. But remember that if we do method 2 or method 3 and we are getting the opposite of what we wanted. So if we did the reasoning and we got a min and the problem was asking for a max, either it means that we did something wrong, or it was actually a closed interval and we were supposed to use method 1.